Okay, so you've just written some awesome Go code. You run it through the compiler, and hey, it gives you the thumbs up, no syntax errors, everything's correct. So you're done, right? Not even close. Because correct is just the starting line. Today, we're going to pull back the curtain and look at the hidden world of the Go compiler to see how it takes your correct code and turns it into fast code.
So if the code is correct, what's the big deal? Well, the problem isn't about correctness anymore, it's all about performance. The compiler's real job is to figure out the absolute fastest way to get your logic to run. And here's the irony. The very structure that makes your code easy for you to read and understand is actually a huge pain for the machine to optimize.
All right, first up, we're looking at the compiler's next problem. It has to take your code, which is basically a story written for humans, and turn it into a puzzle that a machine can actually solve for speed.
So right after you write it, your code exists as something called an abstract syntax tree, or an AST. Now this thing is perfect for checking the rules, making sure your grammar is right. But for optimization, honestly, it's terrible. It's just too cluttered. It cares about things like where you put your curly braces, details that are totally irrelevant for figuring out the fastest execution path.
So what's the solution? Well, the compiler creates a brand new blueprint for your code. It's called intermediate representation, or IR for short. And this is a total game changer, because it gives the compiler a view of your program that is built for one thing, and one thing only: optimization.
Let's think of it this way. The AST is kind of like a paragraph of prose. It's got complex sentences and structure, all designed for a human to understand. But the IR, that's like a set of simple, numbered, step-by-step instructions. There's no ambiguity. Every single little operation is laid out explicitly, ready for a machine to analyze. Take a look at this simple line of Go code, C equals A plus B. For you and me, that's one action. It's simple. But in IR, the compiler lowers it into 4 totally distinct steps. First, get the value of A. Second, get the value of B. Third, add them together. And fourth, store that result in C. This super explicit, step-by-step view is exactly what the compiler needs to find efficiencies. And this is what unlocks the compiler's real power. It can finally ask those critical questions. Questions like, hey, can I reuse this calculation I just did? Does this value ever even change? Wait a second, is this entire chunk of code even reachable? Because if it's not, I'm just going to delete it. You just can't see these kinds of optimization opportunities from the original AST. So now that our code is in this super optimizable IR format, the compiler starts hunting for shortcuts. And one of the biggest performance killers in any program is the simple act of calling a function. So let's see how the compiler tries to get rid of that cost completely. This technique is called inlining. The idea is actually pretty simple, but it's incredibly powerful. Instead of making the program jump over to a function's code, run it, and then jump all the way back, the compiler just takes the code from inside that function and copy-paste it directly where you called it. The function call itself? Poof, it's gone. But the compiler is smart about this. It's not just doing this everywhere. It does a quick little cost-benefit analysis. It asks itself, okay, is the benefit I get from avoiding this function call greater than the cost of actually copy-pasting the code itself? If the function is small and simple, the answer is usually a big yes, and it gets inlined. And this brings us to a really fundamental trade-off in computer science. Inlining makes your program faster, for sure, but it comes at a cost. It makes your final program, the binary file, bigger. Let's dig into exactly why that happens. Okay, first let's see what happens without inlining. The machine code for our little add function exists in exactly one place in the final program. Every time F1, F2, or F3 needs to use it, they all just jump to that single shared location. It's incredibly efficient in terms of space, right? One copy serves everyone. Now, let's see what happens with inlining. The compiler decides our add function is a great candidate. So in the final program, the separate add function is completely gone. Instead, the actual machine code for adding 2 numbers is physically copied and pasted inside of F1 and inside of F2 and inside of F3. The same logic is now duplicated 3 times, which naturally makes the program bigger. And here it is. This is the whole trade-off, laid out right in front of you. Without inlining, you get a smaller binary, but it's a bit slower. With inlining, you get a faster program, but it's bitter. It's this constant balancing act, a decision the compiler is making for you thousands of times in any non-trivial program. And this is really the key takeaway. If you remember one thing, remember this. Inlining makes your binary bigger, because you're duplicating the code at every place it's called, instead of sharing one single copy. It's not magic, it's just a trade-off between sharing and duplicating.
So how does the compiler make this critical decision? It's really important to remember that this isn't some hard and fast rule. It's a very sophisticated optimization. The compiler uses a whole set of heuristics, basically rules of thumb, to decide if inlining is actually worth it in any given spot.
So here's kind of the logic it runs through. If it sees a big, complex function, it's going to say, nope, not worth it. Inlining this would make the code size explode. But if it sees a tiny function that gets called all over the place, that's the perfect candidate. The performance boost from getting rid of all those function calls is totally worth the tiny increase in size. And you have to remember, this is purely an optimization. Your program will work correctly either way. This just changes how fast it runs.
So if you ever need to explain this in a single breath, maybe in a job interview or just to sound smart, here's all you need. IR generation converts the code into a form the compiler can optimize, and inlining replaces small function calls with their actual code to reduce overhead. That's it. That's the one-two punch that makes your Go code fast under the hood. So we've seen the compiler totally reshape our code and start taking these clever shortcuts. The program is now flatter, it's more explicit, and it's ready for speed. But this is far from the end of the story. The very next major puzzle the compiler has to solve is all about memory. For every single variable in your program, it has to decide, should this live on the stack or on the heap? And that decision, well, that has massive performance implications. But we'll have to save that one for next time.